mathematics thing.
I will do my best to. Why I don't.
Is it like-
All right, so we got our exam on Wednesday, so next class. It is, I think I did 16 multiple choice, and then 18 multiple choice, and then 4 what I would call short answers. But short answer is basically just a multiple choice question that I've left open-ended, where you'll kind of like show me your work. So it's not like I'm asking you a definition. It's kind of like the other problems that you would typically see, especially like on the practice exams. You're just going to show me your work so that I can give a little bit of partial credit, even if you don't feel it's completely correct. I mentioned this last week, but I'll print out that formula sheet to be included in every single person's exam. So you all be kind of starting off in the same field when the exam starts. If you want to write on that, once I hand it out to you, that's perfectly fine. So like I think I mentioned, maybe writing down what every formula means on the formula sheet as you're studying. And then once I hand that out, write down the ones that you kind of forget sometimes so that you don't forget, 30 minutes into the exam. We are, I'm trying to think now, is there someone who comes in right? Yeah, there is someone who comes in right after us, but I'll try to eke out as much time as I can. So even though it's like in class 50 minutes, I can probably give us, an extra, 5 minutes before the next class gets in here. If you get here early, if everyone's here, we can start it a little bit early as well. I teach right before this, but I'll come here right afterwards and maybe we can get going a little bit early as well. Okay. Other than that, are there any questions for me kind of just about the logistics of the exam or, okay. So make sure you bring a calculator. That'd be very important. I'll have mine, but if more than one of you forgets it, then it's going to be a little bit problematic. So we'll kind of work through any questions that you guys have now. I don't know if you've gotten to take a look at these exams. If you have specific questions, I'll start with those. Otherwise, I'll kind of pick and choose which ones to go through. Nobody has any? Yeah.
This is a different question. For the variance, we don't, or for the standard deviation, we find the variance. Do we square root each individual part or square root at the end?
Just at the end, right? So if your variance is 100, right, and your square root, so you calculate the variance with that standard deviation, you just take the square root of the variance. Yep. It'd be a lot more of a headache if you had to square every one. Any other questions before I kind of? No? So I know that we did some Bayes theorem stuff last class. I'll work through one of these and kind of show you some questions that aren't on here. So practice exam B, right? This is kind of using that economist, the wages looks thing. So we've got our two events, right? They're making $8 or more, making below $8, being ranked below a 3 or at least a 3. So it doesn't matter what our events are here. We can always find, we've got two events and then their complements. We can build one of these contingency tables where the top 4 left cells all represent what? Intersections, right? So these are just all the intersection of whatever the row and column heading are. Our totals represent the probabilities of the events themselves. So I might have some missing values here. All right, so how could I find X? Yeah.
You just add up 0.1 plus 0.67.
Yeah, we said we can add across the rows or down the columns to reproduce those totals, right? The idea being, for everyone who makes $8 or below, they're either rated below 3 or 3 or above, right? That includes every single person who makes below $8, right? So when we add those across the rows, that's why that works. So here to solve for X, right? We know that 0.11 plus 0.67 has to equal X, right? What's another way we could have found X here as well? So 1 minus 0.22. Yeah, right. We know that the totals have to add up to 1. Okay? Right? If I'm taking everybody that makes $8 or more, and then add that to everybody who makes less than $8, that includes every single person in our data set. Right? So we could have found X several ways. Z, it's the same kind of idea, right? I could have said 0.11 plus Z is 0.13. Or I could have done Z plus 0.2 is equal to 0.22. Hopefully these ones where you have to fill in the missing value, these should be some easier points, right? I don't expect too many people to be missing these unless it's, you make a math error or something like that. So if we do that right, we'll get X is what, 0.78. I'm doing the math in my head correctly here. And then Z would be 0.02, right? So 0.78 for 5 and 0.02, so C for 6, right? So those ones should be easy. I probably won't give you 2 questions like that in the exam because I think both those are relatively easy. What would be the best description for that missing value of Z? So this is where, we're just thinking about what do these cells represent? And Z is going to represent to us the probability that someone is making at least $8 an hour and their kind of looks were rated a 3 or below a 3 here. Okay. So kind of remembering those are the intersections, right? So what's the probability that an individual has looks of at least 3 or a wage of $8 per hour? So this is one where, let's see if I can remember this. So at least 3 below 8. So what we're looking for is we want, and I think it always helps on these, just write out what you're looking for. So the probability that wage is at least $8 and, right, we had that looks, I think it was above 3, we'll see. Right? That's what we were looking for, right? We're looking for the probability of this, it wasn't and, was it? It was or, right? So we've got a union of these 2 things. So I can think of this as my event A, and this is my event B. I might not remember off the top of my head, but when I want to find the union of 2 events, I go to my formula sheet. Oh yeah, that was when I just added the probability of each event, but then I had to subtract what I double counted, which was my intersection. So we're going to find the probability of each one of our events and subtract out their intersection. So if we go back to our practice exam, I'm going to make sure I got this right. So it looks at least 3 and wage below 8. Okay. So here, I wanted to rewrite this as the probability of A. So wage is at least $8 plus the probability of B. That was 3, and then minus the intersection. So at least 8 and looks greater than or equal to 3. So what's the probability the wage is at least $8 an hour? I just go to my total column. So 0.22. What's the probability if I selected this person at random that looks was above or equal to 3? Go down to that total of 0.87. And then what's the probability of the intersection of the 2? That would just be 0.2. Okay. So we subtract 0.2. This should be 0.89. Any questions on that one? So I might ask you to find like the intersection using a contingency table. That's really easy. It's just one of those top 4 left cells, depending on what I'm asking for. The union is a little bit more work, right? Where I have to find the probability of each event and then subtract out the intersection. Now I could have done it the non-technical way as well. You remember that? I'm going to waste a lot of time on it. But if I look at the intersection of these 2 events, and then I made the L and added those up, that would have also got me the same thing, which is what, 0.89. Just remember Z was 0.02. I wouldn't try to remember it that way. I mean, you can, but I think that's kind of more of a fail-safe way is using the actual formula. Right? Any questions on anything up to that point? All right, do I have a conditional one here? Hopefully I do. Yeah, here's a good one. So even though we're not directly given this on the table, we can find conditional probabilities as well. So I've got, what's the probability an individual makes $8 or more, or above $8, given that they have looks like greater than or equal to 3. So this is where we're thinking about, I've got conditional probability. So I'm conditioning on, the given there is that looks are at least 3, or greater than or equal to 3. So that's where I set up the terminology. I'll make sure I use on the exam and use this word given. Right? So it makes it a little bit easier to identify what we're conditioning. Once we condition on that, we want to know probably that the wage is above $8. So we think about, here's our event, A and B. We can't remember how to find a conditional probability. We go to the table. Got this guy here. And it reminds us that it's just the intersection of the two events divided by whatever we're conditioning on. So I would write this out, right? Wage of 8 and looks greater than or equal to 3. And I divide by, remember, what I'm conditioning on is what's on the right-hand side of that line. Right? So divide by the probability that looks are greater than or equal to 3. Now, these two components I can find in my contingency table, right? So I go back. What's the probability that I see someone making at least or above $8 an hour? And the looks are at least 3. So that intersection is 0.2, right? And then I would divide that by the probability that I such something random, the looks were greater than or equal to 3, which is what, 0.87 here. So 0.2 divided by 0.87. Someone's going to have to help me with the math in my head there. 0.2 over 0.87, is that 0.23 approximately? Okay. Any questions on this one? So I can guarantee you I'll ask you to find a conditional probability using a contingency table. So I have this exact same setup. Yeah.
Why do you know what to use the contingency intersection over like the
Okay, so how do I know when I'm looking for this conditional probability that I can use the intersection divided by what I'm conditioning on as opposed to Bayes' theorem? Is that kind of what you're getting at? Yeah. So non-technical answer is, notice in the practice exams, I have a pretty similar way in which I order the questions. So you'll probably have to use something like this before you get to that Bayes' theorem. Right? Now you can try to write those Bayes' theorems examples out using this general form of the equation, and you'll quickly realize I don't have these probabilities. For instance, if I were to use some of the examples that we had before, I think last class, did we do a baseball steroids on last class? Is that what we did? So it'd be something like, given that the test comes back that they were positive for steroids, what's the probability they're using? Right? So I tried to write this out using the definition I did over there. And what I'll quickly realize is, especially from my denominator, is I would never given just a probability the test comes back positive. I have a bunch of conditional probabilities that the test will come back positive for different individuals. But whenever I try to write out a Bayes' theorem example using that kind of easier version or easier formula, I'll always realize, oh yeah, I don't have this probability, which is why I need to like break this up into the group of people who tested positive and we're using, people who tested positive and not using. And then in order to find those, I have to use my conditional probabilities, and that's why it's a little bit more. So you can try to write out a Bayes' theorem one using that, but you'll just quickly realize this can't be right because I don't have these probabilities. Does that answer? I feel I'm talking very fast. That's why I apologize. But you need to slow me down. Make sure you do. Any other questions as people can do some of these? So I think I included these on this one, did I? Okay. So I had a whole different kind of setup. But we might break this up into several questions, but regardless, we're interested in the definitions of mutually exclusive and independence. So if two events are mutually exclusive, what does that mean? It don't have to be the most technical description, but if two things are mutually exclusive, that means what? Yeah. Yeah, there's no intersection, right? They can't happen at the same time. So if we're thinking about any two events being mutually exclusive, that means the intersection is equal to 0, which if I look at a contingency table, I can identify that very quickly, right? The only way that two events are mutually exclusive is if when I look at their intersection in that table, I see a 0. Right? Even if I don't know which one I'm looking for here, there's no 0 in this contingency table. It doesn't matter which events you're asking me about, they're all going to be mutually exclusive. Sorry, they're all going to not be mutually exclusive, right? So I don't see any zeros, right? So even if I'm thinking about A and B complement, well, their intersection is 0.3, so they can't be mutually exclusive. Right? So in a question like this, right away, I know that it either has to be D or B, right? Because A and C are both stating that those two things are mutually exclusive. I know they're not. There isn't a 0 for their intersection. The second thing I need to check is, okay, are the complements independent? Right? So this gets a little bit tricky, but for independence, we would say two events are independent, and here I'll use the complement, if the probability of that event is equal to the probability of that event given the event you're wondering if it's independent from. Right? So we still are going to be looking at the unconditional probability of a complement. If that's the same as the conditional probability of a complement, right? So when we talk about these conditional probabilities, we're conditioning on B complement here, that B complement has occurred. But we're still looking for the probability that A complement happens. Right? So we're thinking about the unconditional probability of A complement. It's whatever's on the left-hand side, that's what you're finding the unconditional probability of. What's on the right-hand side is what you're conditioning on. Okay? So when I start to compare these, so there's like, I think in the other practice exam, it's something like some of your options would be just, if we're just worried, are they independent? You can't say something like this. Well, you shouldn't say something like this. This doesn't have to be anything, right? Because here I'm comparing the unconditional probability of A complement to the conditional probability of B complement. That tells me nothing about independence. I have to be looking at the same event in my conditional and my unconditional probability. So I need to check to see if these two things are equal, right? So once again, right, I'm going to have to find this conditional probability by taking the intersection of those two events and divide by what I'm conditioning on. Okay, same step we had before. So what's the probability of A and B complement there? 0.3. What's the probability of just B complement? 0.75. What does that work out to be? Is that 0.4? All right, so the conditional probability of A complement is 0.4. What's the unconditional probability of A complement? 0.4. So this actually happens to be one where these two events are independent, right? Those probabilities are exactly the same. Doesn't matter if I know that B complement has occurred or not, the underlying probability of A complement has not changed. So I would say that what? They are independent, but not mutually exclusive. So these, events can be mutually exclusive and not independent. And that's totally possible. We just have a situation where that's the case. Okay. Think about this for a second. Can an event be mutually exclusive and independent? So if two events were mutually exclusive, what has to be true? The intersection is 0. So then when I go to find one of these conditional probabilities, what's the conditional probability always going to be? 0, which as long as the probability of the event itself is anything above 0, which I don't know why I would ever have an example where they wouldn't be, right? That'd be a very uninteresting example. Then you actually couldn't have, right, two events being independent if they're mutually exclusive. Yeah. But I wouldn't ask you with it. That's a lot more of a thought kind of experiment than an actual question I ask. But we can, it kind of helps us break down what we're actually doing with this idea of mutually exclusive and independent. I would also suggest if you're concerned about Bayes' theorem problems, I don't like exam B's near as much as I like exam A's and the additional exam C that I put up. So I would focus on B and C's Bayes' theorem examples way before I get too involved into those set of questions that are looking at Bayes' theorem for that. It's much more likely to phrase them the way I did here in exam B and C. Okay. But so we'll kind of skip those just for, oh, where am I at? I'm in exam B. So we'll skip those for now. I wanted to point something out. I think it's probably worth going over some binomial and Poisson stuff, maybe even some uniform questions here. But I wanted to point something out that I usually do up here. So you'll see, like in practice exam B, I just ask you to calculate a population variance based off of, some sample data set. It is more likely, I've written the exam's printed, so it's 100 probability of 1, that I would be more likely to give you something like this. And then I'll ask you when I ask you to find a standard deviation or to find a variance. Obviously, if you didn't calculate the mean correct, you can't get the variance correct. So it's way more likely that I'm going to ask you to find a variance. I'll give you an assumed true mean, right? So I'm here to say if the average height, or I'll say assume the mean is equal to this value. Right? And then what you'll do is you'll calculate your variance or standard deviation, kind of finding your deviation from this mean, right? Even if this isn't the true mean based off the data. Whatever value I'm giving you here to assume true. That way we don't get cascading errors, right? If I ask you to find the mean, I ask you to find the variance, but you got the mean wrong. Now you got 2 questions wrong because of one, mistakes in one. So I'll do that a lot right here. And then usually if I'm asking you about a discrete random variable, like down here, notice here I give you an assumed true mean of 2, right? Even though I asked you in 14 to find that. So I'll give you these assumed true values some of the time. So read the questions carefully. Just because you're confident in the mean that you found for 14, make sure you don't keep using that mean in the next problem, because I might be giving you an assumed true mean now. Make sure everyone's kind of starting off on the same point. Okay. So I just wanted to point that out before I forgot. Are there any kinds of questions you guys would rather see binomial, or do you want me to go through calculating a variance or a weight or of a discrete random variable or a weighted mean? No one has any? Zero preferences? I need some indifference curves here, people. Like, what do you want? So, no, I'm just joking. But let's go back here. Let's walk through. Let's do one like this. So this is practice exam C. Okay. So number 4 kind of gives you student score in different categories. It tells you the weight of each of these categories. So, part of what I like about this class is that when you teach weighted means, that's kind of how you guys can calculate your own grade, especially at the end of the semester, right? So if you know the weight of every category, and then you've got your score in each one, you should be able to determine your grade even if the different categories are weighted differently, right? So here I've got quizzes are 20%, homework's are 40, midterm is 15, final exam is 25% of your overall grade. You've got the student scores in these different categories. What should the student's final grade essentially, in this weighted score being applied? Well, first of all, which of these don't make any sense? Yeah. I mean, 321 for sure makes no sense, just in the context of like, if I'm finding someone's grade in the course, I mean, I've had people get A+ before. I've never had someone get a 321% in the course, right? Like, that doesn't make any sense. So right away, I can rule that out. Right? Any other values that can move up here? 45.61. Yeah, right. Same idea. I know I'm finding a mean. I'm finding the middle point of the data, or in this case, the middle point of kind of my different scores. Well, if my highest score on the homework was 94, but my lowest score came from the final, which was 68. The middle point of the data has to be somewhere between those values. So A and D make no sense at all here. So right away, I've got a 50% shot of getting this one right, even if I spend literally no time. I mean, I just had to spend the time to figure out how to cross those two answers out. But I've now got a 50-50 shot even from just guessing. So I do that a lot. Like that's what I think is what I like multiple choice exams a little bit more, especially like in the stats course, is as long as you know the principles, a lot of times you can just make a guess. Like you can go from a 25% chance of getting it correct to a 50% chance just by understanding the principles behind what you're doing, right? So it doesn't require you to like make the correct calculation or choose the correct formula. You need to be thinking about what you're doing first, and then that allows you to have a much higher chance. You can guess. So from here, I'll show you the formula sheet when I go back over there. But we've got our equation for a weighted mean, right? Being something like this. Okay. So here I'm looking at the score as my variable, and the weights are going to be the weight of that category. Kind of makes this one a little bit easier. Okay. So I'll go through, take the weight, multiply it by that X value, add to that the next category's weight of 40, multiply it by the score I got in that. It's the worst thing about masking a beard. Sometimes I get beard hairs like in my mouth. So we got a score of 94. The next category weight is 15. 84 was my score in that category. 25 for the final exam, multiplied by the value or the score I got in the final. And now, if I add those up, I'm going to go out on a limb and guess that if I add all that up, I'm going to get 321, right? Because what did I not yet do? I still need to divide by the sum of my weights, right? Now, the sum of my weights here is pretty easy. If I look at them and I think about the graded course, hopefully this adds up to 100%, right? Maybe it doesn't have 321, I could be wrong, but 40 was 60, was 15, was 25. The sum of my weights here should be 100. You probably know you can't end up with 300. But, so if I do this, I think, if I remember correctly, I think this is 82.2. You're kind of following along with me, and that's not right, let me know, but I'm pretty sure that's what it is. Questions on that? Yeah.
Do you also make those like percents or like 0.2 decimals and then just add them up and?
Yeah, if you want to. So this is the kind of formula I'll give you for the weighted variance weighted mean on the formula sheet. Another way to think about this is if the denominator is always the same, this is really the weight I could use instead of 20 is 20 out of 100, 40 over 100, 50 out, which makes it a lot more like when we were finding the mean for a discrete random variable. Because what you're essentially doing there is you're turning the weights by dividing them all by the sum of the weights first. You would be making each one kind of like a probability, so that the sum of them should always be equal to 1. So you don't have a denominator. You can just use those weights as well. Yeah, that's fine. Yeah, that's easier for you to think about, right? That's perfectly good. Now, that's really easy to do when it's something like 100. If you have something where the number works out a little bit different, it's probably not quite as easy to do it that way. But yeah, for sure you can do it that way. Any other questions? No? Okay. Let's think about some uniform distribution stuff. Which I know is down here. Oh, wrong exam. Go back to practice exam B. I think that's where the uniform stuff was. There we go. So let's say you're waiting in line at a roller coaster. So the amount of time you can wait is 15 minutes at lowest and 75 at its highest. So we've got this uniform distributed variable that goes from 15 to 75. Anytime I see uniform distribution example, right away, I make a drawing and I think about here's my minimum, here's my maximum. On top of this, I could actually add in some additional information, which I don't need to for this first problem, but I automatically know what the height of my distribution is going to be. So one way to remember the height if I look at my formula sheet, so here was my weighted mean, by the way, kind of over here, and then a weighted variance. But I'm thinking about the uniform distribution problem or formulas, they're going to be these down here. So here's my mean, variance, how I find the probability of being in between two values. And this is kind of a reminder of everything's equally as likely. So the height ends up being 1 over d minus c, which we're really saying there is 1 over my minimum minus my maximum, or 1 over my range. So here, 1 over 75 minus 15, or 1/60th. That's the height of my uniform distribution. Everyone okay with that? So I then might ask, what is the mean expected wait time? So the mean, we said everything's equally as likely, so it's really just finding that middle point. Right? Now we're reminded in the formula sheet that to find that mean, you just add up the minimum and the maximum and divide by 2. So if we take 75 plus 15, divide by 2, we should get 45. Okay with that one? That wasn't too bad. If I wanted the variance, right, all I have to do is take the range, right, the difference between my maximum and minimum, square it and divide by 12. So that would be what? 75 minus 15 squared, divide by 12. I don't know if this is right, but I think I might be looking at this wrong. I think it's 100. No, it's not 100. What is it? So it'd be 300, 3,600 divided by 12. Okay. Now that was the variance. If I wanted to, so this is a variance. Going back to an earlier question, if I want the standard deviation, square root of 300, right? Which is that going to be 17.32? Okay. So read these problems carefully, because when it comes to the exam, I might ask you for the standard deviation here. And then earlier, if I asked you for the standard deviation, I might ask you for the variance in an earlier problem. Like those are the things I can kind of alter throughout the exam relative to the practice exams. Okay with that. So if I ask you like for means and variances of this should be pretty easy points, hopefully. Because I mean, I'm telling you it's a uniformly distributed variable. This is even easier than the binomial because I have to tell you that it's a uniformly distributed variable. Here's your uniform distribution problem or equations that are on that second page. There's your mean, there's your variance. Okay. So what if I wanted the probability that you wait in line for more than 50 minutes? So this is where drawing these out, I think really helps. So you know where the mean is at. And now I'm telling you, what's the probability you wait longer than 50 minutes, okay? Automatically, what do you know this probability has to be less than? Well, that definitely has to be less than 1, right? No, I mean, he's not wrong, right? I gave you a ridiculous answer up here, right? So 1.25 you can rule out right away. But it also has to be less than what value? 0.5. Why?
It's less than half. It's less than the mean, like.
Yep. So the mean is going to exactly split this in half because it's like everything's equally as likely. It ends up being a symmetric distribution. We said it folds on top of itself up if you use the mean. So the area to the left and the right of the mean is 0.5. So it's almost like I thought about the blue area. That area is 0.5. I want something that's smaller than that, right? So right away, I've got it narrowed down these two answers. If I'm just going to guess here, 50 is pretty close to 45, right? So I'm going to guess the area is pretty close to 0.5, right? So if I'm guessing here, D is probably what I'm going to go with. but I can actually figure out if I gave you answers that were a little bit more similar, right? So all I'm going to do is I'm trying to find the area of this rectangle, right? The height I know is 1/60. The base of this rectangle is, well, it goes from 75 to 50. So multiply those two. Now I could use the formula, right, that I have in the formula sheet, plugging in where my interval starts and stops, A and B, plugging in the maximum and the minimum. But if I started this problem out, identifying my height of the distribution and just thinking about, okay, I'm just finding the area of a rectangle. Height times kind of the base or whatever. Well, it becomes a lot easier. I think it's a lot easier to do it this way, especially if you have the visual. The visual helps you out. Think about, can I say this is less than 0.5? You know, or is it greater than 0.5? What if I ask you, what's the probability that you wait longer than, 25 minutes? Well, now I know that has to be greater than 0.5, right? So the visual really helps with it. And sure enough, I believe this does end up being that 0.42. Any questions on that one? All right, so I'm going to change this one because I know that I would write this a little bit different. So I've got up here, what's the probability somebody waits between 30 and 45 minutes? What I might be likely to do on the exam is something like, what's the probability that, wait, I did 30 and 45? It's probably that they wait between 30 and 45 minutes, or that they're waiting between no, I can't do that. Hold on. There we go. Something like this. So if I think about visually what I'm looking for here, I have the same setup, same height. I start at 75 to 15, and I wanted the probability being between 30 and 45, or between 60 and 75. Okay. So I'm going to find this one first, and I would do the exact same way I did over there. Right? I've got the height of my rectangle is 160. The interval I'm looking at goes from 45 to 30. So that's what? 15 over 60. 0.25. Questions up to that point? If I can save myself a lot of time, what has to be this area? It's the same interval. It's the same height. It's the same length interval. So every interval of the same length in the uniform distribution have the exact same probability, right? Have the same base and the same height. As long as they don't overlap, right? These two don't overlap, so there's no intersection. I just subtract out the intersection. So all I have to do is add this area to this area, and the probability that I wait either between 30 and 45 or between 60 and 75 would just be 0.25 plus 0.25 or equal to 0.5. So I might ask you to find like two areas, right? Two different intervals and then add them together. And usually when I do that, I keep the intervals in the same. So if you can remember that feature of the uniform distribution, it makes that calculation a little bit easier. You can save yourself a little bit. Any questions on that? I add a little bit for this problem. So that's the uniform distribution. I think that might be the last one I have here. Yeah. I'm going to we'll use this one. I kind of want to do, yeah, we'll do this one. So let's say 20% of Americans go without medical care because of cost concerns. Suppose we get 10 people at random. What would the mean and the standard deviation of this variable be? So we've got 10 people. Probably any one person doesn't have medical care is 0.2. Right? So I've got successes that they go without medical care, which is kind of weird, but that's what I'm looking for. And the failure rate, they don't. I'm capped at the number of people, which is 10. I have the same underlying probability of success when I'm looking at any one person. So this is a perfect situation where I can use that binomial distribution. Okay? So I go to my formula sheet, and I have this set, notice kind of bracketing things that go together. So I've got this set of equations that are my binomial distribution. So I've got my mean and my variance equation here. The mean is simply n times p, and the variance is n times p times 1 minus p. Okay? So I go back here. What was my number of trials here? 10. So the n is 10. What's my underlying probability of success? So the mean should be a pretty easy one. N times p, n times 0.2. Which is 2, right? And then we said the variance is n times p times 1 minus p. So 10 times 0.2 times 0.8. So 1.6, if I'm doing this in my head correctly. Which, that's the variance. So the answer to 14 is just 1.6, right? I'm looking for the standard deviation. Right? So we're going to make sure we read carefully. So I got the variance. From there, I need to take the square root to get my standard deviation. Right? So the square root of 1.6. I don't know. Is it 1.26? Questions on that one? So once again, I probably won't make that 2 individual problems because these should be like easier points. Right? Identifying that set of binomial equations, that mean and variance should be not too bad. So then the next one is, what's the probability that exactly 5 people go without medical coverage? So if I'm looking at these, sometimes the way I'll write these in, I won't do something like this. If the answer ends up being kind of past whatever decimals I'm displaying, I'll usually use the terminology of approximately 0, right? So I'm put 0, 0, 0 up there because it could be that it's like 0.0001 or something, but I will kind of use the term of approximately 0. And that's really anything that you see the first 3 decimals being probably 0. Anything where I have to go all the way out to the 4th decimal. But I want the probability that x is equal to 5 here. Before I even go to that formula, because I can go, okay, I got to use this, plug all my values in, right? That's the process. But I just stop and think about this. What's the most likely outcome I see in this example? Well, the mean is 2, right? We said the mean tells us kind of what the most likely outcome is going to be. So it's going to have the highest probability of occurring. As I go in either direction, the probabilities are going to start declining, right? So now it's not easy to visualize how quickly they'll decline. But if I stop and think about this, which of these answers could I rule out? D, C, I can't theoretically rule out. I'll explain why in a second. But why can I rule out B and D right away? So it's not that, right? B is not the mean. Remember, the mean is 2. Okay? So 2 will be the most likely outcome. But we don't know what that probability is. The most likely outcome could have a probability of only 0.2 or 0.3. So if we're looking for the probability of 5, if it in fact was 0.9 or 0.5, it'd be theoretically impossible for 2 to be more likely than 5. Because all these probabilities have to add up to 1. So if you're telling me the probability of 5 is 0.9, at most the probability that 2 can be is 0.1, which makes it not the most likely outcome, which we know it will be the most likely outcome. Same kind of idea with 0.5, because if 5 has a probability of occurring, at most 2 would have the probability of 0.5, which we know also it can't be because these other values in between 2 and 5 have to have some non-zero probability. So right away, answers as high as B and D don't make sense. Now, if you wanted to tell me that C doesn't make sense, possibly. But like I said, let's be careful because I don't know how quickly these probabilities are falling. In some of the examples we did, I remember the most likely outcome was like 0.17 and it fell to like 0.02 and then just moving over one, and then it fell like 0.02. So they can fall really quick. So just because you see really small probabilities, I wouldn't rule them out right away, especially when, we are like 3 values away from that mean, and we really can only go to 10, right? But I would agree. If I'm guessing, A is probably the most likely outcome. I don't know for sure, right? So we start plugging our values in at the n factorial divided by x factorial and minus x factorial, probability of success to the x power times 1 minus the probability of success to the n minus x. Here's where I would do the easy math in my head. Maybe replace this with what? 0.8 to the 5th. It's a little bit easier to get put in my calculator. Probably do some things where I can cancel some of these values out, or I can use that factorial button in my calculator if I have it and I'm comfortable using it. Really at this point, it's just a matter of being comfortable kind of using your calculator, whether or not you want to do it all in one line or kind of break it down into 3 values and then multiply those together. Steve, any questions on that? I don't remember what that ends up working out to be. Is it 0.02? Okay, that sounds about right. What is it, 0.2 to the 5th? Yeah, 0.0264. So notice this is a good one where a lot of times I'm going to be rounding these values, but I'm never going to give you something like 0.026 and 0.0027 where the rounding error kind of just so happens to be the wrong one. Will always be different enough where that the rounding shouldn't cause you to identify the incorrect answer. I don't have time to completely work through this, but I'll at least set kind of the idea up so we can think about this. So what if I wanted to find out probably at least 2 people going out for medical healthcare coverage? This is where I think just writing it out helps, right? So at least 2, we said, well, what's the probability that X is greater than or equal to 2? Well, that's the probability that's 2, plus the probability that's equal to 3, plus 4, 5, 6, all the way to 10. In a short amount of time, I doubt I expect to use that binomial equation like 8 different times. So what can we probably do if we think about this as event A? We know that any event is equal to 1 minus its complement. What's its complement here? Yeah, X is less than 2. This could be complete, but you're right. Heard a lot of you saying, what are the only outcomes that fit this criteria? The first one would be that X is equal to 1. Next one would be X is equal to 0. Well, that's as low as we can see as 0 successes. And now we have to use that binomial equation only twice and then subtract. I want to point some out if we have at least another minute or 2. Okay, I'll point this out then on this one. So if I'm thinking about this, right away, what should this probability, should it be closer to 1 or closer to 0? Go ahead and guess. I would think it'd be a little closer to 1 if it was me, only because 2 or greater, you're including the most common outcome, and then like 7 of the other outcomes opposed to only kind of losing out on 2 of them. Now, these 2 outcomes are more likely than the ones out here, but I mean, I'm guessing it's probably going to be something that's closer to 1 than 0. I don't know what it ends up working out to be. My guess is the answer here is B, just because it is a little bit closer to 1 than 0. It wouldn't surprise me if maybe A is the right answer, but I would be thinking it's probably something that's a little bit closer to 1 than 0. For it to be B or C really doesn't make a lot of sense, just because it includes the most common outcome and a lot of the other kind of outcomes near it, plus a lot more outcomes out here on the right-hand side than we have kind of counterparts for on the left-hand side. So when you're looking and thinking about these, often think through those things as well, right? You know, these answers are all kind of reasonable, but if I put something up here like 0.002, that doesn't really make a whole lot of sense, right? It includes the most common outcome. We can probably rule that one out. So we'll kind of leave it there. I will be in my office today. My office hours are usually 2:30 to 3:30. I'll be there a little bit later if you do want to stop by from like closer to like a little bit before 3 until a little bit before 4. So just kind of shifting them forward a little bit. I'll be around a lot tomorrow during my office hours for sure, 11 to 1. But if you want to meet at any other point in time, shoot me an email. I have a meeting at 1, but that's about it. So I can kind of schedule things if you got some problems you're trying to last minute get answered. Okay. All right. Good luck studying. Like I said, feel free to reach out, and I will see you guys in class for the exam on Wednesday.